now let me derive something that you probably haven't seen before. So of course, the Coulomb potential, I mean, what can be more boring than that? So let's study interactions that are a little bit different. So namely, we will study interactions of Yukawa type. So suppose we have a theory of some fermions that are interacting with a scalar field through this pair interaction. So there is a term of interaction between psi bar psi and the phi. So this can be regarded as an oversimplified model of strong interactions. So if psi bar describe proton and neutron, phi describes pi mesons. This would be a sort of, I mean, one has to decorate this a little bit to get a more realistic model, but these salient features can be seen just from this very simple schematic picture, a schematic model. So when we do the same thing, so let's consider the scattering of these fermions on each other. And so, okay, so what are the Feynman rules for this theory? Well, we need to, so the interaction, Lagrangian determines what are the vertices of interaction, right? So here at each vertex, we will have one fermion line and one anti-fermion line, one fermion line coming in, one fermion line going out, and the scalar line joining this vertex. And let me draw scalars in a broken line just to distinguish them from fermions. So we will study now the process of well, scattering through this interaction. So let's first study psi of same charge, scattering of same charge particles. And so this will be described by two diagrams where the photon line is replaced by the scalar line, and this will be the only difference, right? Okay. Well, let me not do this computation again. So the only difference here is in the propagator factor for the particles that carries the, which is the force carrier. Okay. So let's see. So the vertex then comes with the factor of minus Ig. Right? And no gamma matrix. So compared to electromagnetic interactions, what we will get is that minus Ig mu nu. Oh, in fact, let's compute this amplitude in U. So what we'll need to do is, first of all, we need to get rid of the gamma matrices. So this will be 1 minus I over G minus IG squared. Then U bar S of P, U S prime of P prime. Then U bar R of K, U R prime of K prime. And then we will have the scalar propagator. Instead of the photon propagator. So this is the answer for the amplitude. And so, okay, so there are few differences here. Okay, so we will assume that the momentum, so the momenta here will be of order of the scalar mass, but much smaller than the fermion mass. So we assume that fermions are heavy, like proton and neutron are very heavy particles, but the scalar is assumed to be lighter. So for instance, the pion is about 10 times lighter than, or 8 times lighter than nucleons. So, so in the potential, we will do the same relativistic approximation for fermions, but we will not neglect the mass correction here in the propagator. So at the end, what we will need to do is we will need to compute the matrix element of non-relativistic spinors U bar S times U S prime. So this will be equal to what? To well, this is equal to 2m delta SS prime for always. So we computed this matrix element once, and there is no difference here. So at the end, what we will get for the amplitude is it will be the same as in QED, but let's see. So the difference will be that there will be some mass dependence in the denominator. So where do we have the formula for? So over there we have the formula for the amplitude in QED. But the formula in Yukawa theory will be with the plus sign. So why with the plus sign? Well, times the spinor delta functions. Why this y plus? Well, the reason is that here we have a plus. So for the scalar, the propagator comes in with the plus, while for photon it comes in with the minus. So this minus is the same, can be traced to the difference of signs in the propagator. Now if we consider the scattering of opposite charges, well, this arrow should go. So again, this diagram is very small. In this diagram, so compared to the QED case, so here we have, we use the fact that UU bar is 2m, S prime, delta, S prime, but V bar, VR, V R prime is also 2m with the plus. So this sign is important here. You see that the minus here arises because the spinors, so the so I think I a little bit skipped this point, but here the overall sign depends on the fact that V R gamma 0 V R prime is equal to V bar R V dagger R V R prime, which is minus 2m delta R R prime. So the charge density of electrons is the minus of the charge density of positrons. So they have different charge density. But this relativistic product of spin array functions does not change sign between electrons and positrons. It's always normalized to the plus 2 times m. So this is a crucial difference. This means that the potential that will, the amplitude that will compute here is the same as for the scattering of the like charges. So there's no sign change. So the potential of interaction due to exchanges of scalars is the same for like charges and opposite charges. And so let's compute what it is. Yes?
Shouldn't there be a factor of -1 due to the exchange of the wick contraction?
No. Well, I mean, we are comparing signs between the scalar and vector exchanges, and so the only sign change is here. So we or I'm sorry. So here there is one sign change here because the propagator has different sign. So here there will be two sign changes, one due to propagator and 1 due to this plus here. So the sign will be the same as for the vector exchange. So all in all, the sign of interaction will be the same in this case. So it will be attraction. And so we conclude that scalar particles mediate universally attractive interactions. So Yukawa interactions are universally attractive. And we can compute the potential. So the non-relativistic potential of Yukawa interactions is equal to, well, the Fourier transform of what remains of the scalar propagator. So if you do the integral, you get, well, the Coulomb potential multiplied by the damping exponential that kills off the interaction at large distances. So you see that the potential is short distance. And is attractive. So it dies off at scales. There is a correlation length which is coincides with the Compton wavelengths of the scalar particle. So what we get is short-ranged universally attractive interactions, and this will qualitatively explains why nuclear forces are such as they are. So they are very strong and attractive at short distances. The four, okay, nucleons, I mean, nuclei can form from protons and neutrons, because otherwise, okay, proton has positive charge, right? So it's there is a Coulomb repulsion between protons that they can still form bound states, because the nuclear forces are much stronger, and at short, but they act only at short distances. So there is no macroscopic remnant of them. They die out on scales which are, well, roughly speaking, of the same order of magnitude as nuclear, as size of a nuclei. Now, why are they stronger? Well, in this semi-schematic picture, that arises because this interaction constant is 10 to the 4 times bigger than the electromagnetic charge. Because G is dimensionless, and it's roughly speaking something like 13 or I mean, it's a number of order 10. Yes. So you had some question? What did I forget? In this formula? Oh, yes, of course. Thank you. So we have the following pattern. So if we have so Yukawa interactions that are mediated by spin 1 particle, spin 0 particle. So this gives, well, Yukawa interactions, and they describe nuclear forces. So the interactions are universally attractive. If the mediator has spin 1, as in electrodynamics, so the Coulomb potential can be both attractive and repulsive, depending on what sign of charges we consider. Oh, by the way, one may wonder if this type of scalar interactions, could they be actually repulsive? Well, and you can see that they couldn't, because if you change the sign of G squared will still be positive. So to make them repulsive, we should have made G imaginary, but then the Lagrangian density would be pure imaginary, and so this would correspond to imaginary Hamiltonian, which is bad. It's not consistent with, say, unitarity of time evolution. Yes. Because this is the 4, so this would be energy minus energy prime minus momentum prime minus m phi squared. So I forget about this. This is small. So because of that, I get one of the minuses that.
Another question is, so I noticed that for the same charge scattering, you considered the exchange of the out state.
Yes.
But for the opposite charge scattering, you don't.
Because they're distinguishable. So these are really different particles. They have the opposite charge. So you can tell which one is which.
So that diagram doesn't exist.
The diagram doesn't exist. Electron cannot become a positron. So anyway, well, can we continue this table? Well, certainly we can add at least one row because we know very well what is the spin 1 particle. Yes. Because, okay, so the for momentum flowing through the scalar propagator will be the sum of energies of the central mass energies of the colliding particles, and which is by order of magnitude is equal to their twice their rest mass. And we assume that the rest mass is much bigger than any other scale in the problem. So, and this will stand in the denominator, so this diagram will be much, much smaller. By the same reason as it is in QD. Yes? Just let me finish.
In the case of Coulomb equation, what happens if the momentum of two incoming electrons are the same?
In which case? Here? Oh, it will. The amplitude will become infinite. Yes, so the Coulomb interaction is really singular in that case, right? So if you let one, I mean, so particle, because the Coulomb interaction is, well, it's singular in the most direct sense, right? So the potential turns to infinity at 0.
We don't have the illusion of the two electrons with the same momentum.
This simply means, so this is, you see that P prime is the momentum of the same particle. So this is final momentum of electron. So this formula tells us that if you send an electron on a Coulomb, I mean, in a Coulomb potential, it will definitely change its velocity. So its velocity change must be non-zero, because otherwise the amplitude would blow up. So, and this is because the Coulomb, this actually has to do, in fact, my first answer was not quite correct. So this has to do with the long tail of the Coulomb interactions at large distances. So the Coulomb potential dies out at large distances too slowly. And so even if you send an electron with a very, very small velocity, it will be deflected by the Coulomb potential. So its final momentum will, you can see this even in classical theory. So this just tells us that Coulomb potential will deflect arbitrarily slow electron. So for instance, if you have some very localized potential, like Yukawa potential, and you send a particle that would, I mean, with classical path that goes very, very far from the scattering center, then it will almost, I mean, it will not change its velocity very much. And so in quantum mechanics, the scattering probability is non-singular in the limit where the momentum change is 0. But for the Coulomb potential, this is not the case. And this has to do with this slow decrease of the potential at infinity. Yes?
Okay, I still don't quite get why for the case of the scalar, U bar U and U bar V have the same sign, and they have opposite signs for photons.
Okay, that is a result of the calculation that we have done sort of in the beginning of the course when we studied solutions of the Dirac equation. So solutions of the Dirac equation for the electron so for the electron, U in the non-relativistic approximation is square root m psi s psi s. Now for the positron, this is square root m psi s minus psi s. So if you compute U bar s gamma 0, US, this is US dagger US, I'll let prime here. So this will be 2m delta SS prime. So the same is true for the positron. Okay, because, okay, so this is just the normalization of this for spinor in the most literal sense. Now, if we compute U bar S U S prime without the gamma, so this means that we insert a gamma 0 between the normally conjugate spinor. So this will be equal to m psi s dagger psi s dagger. So here we will have gamma 0, which is off diagonal unit matrix. Psi s. This is still 2m delta ss prime. For the positrons,
Okay, I see it then.
yes, you'll have a minus sign because
Okay.
of this minus.
Okay.
So this will be 2 minus 2m delta ss prime.
Okay.
So I'm sorry. So here there is a plus. Right. So there was a plus here.
Yeah.
But there is a minus. There is an extra minus in the Yukawa calculation because of this. So think that you close this up. So actually, this sign changes. There will be a minus here.
That's kind of what I was thinking it should be. But
Yeah, that's
Yeah.
sign error I was asking about.
yeah.
I think at least I think that's what the source was.
Let's go back and see. So compared to electron positron scattering on photons, so we have one sign change in the wave function in the matrix element. So this is one minus. The other minus is here.
No, I don't dispute that that as before it would be this way. No.
Just hold on. And
No, I think everything looks
so there will be two sign changes in the case of particles with opposite charges scattering on each other. So opposite particles will have the same sign of interactions. Okay, so this is what we are getting here. So the potential is attractive for opposite charges. So it has the same sign as electromagnetic interaction. So then if you count signs for the like charges, there will be just one sign change here and no sign change in the matrix elements. So we'll pick up an extra minus. So anyway, so what is spin 2 interaction? What are spin 2 particles? Gravitons. So this is the gravitational interaction. And that's universally attractive. So the pattern actually must be clear from these three examples that even spins produce universally attractive interactions, and exchange of particles without spin may produce attractive or repulsive interaction, depending on whether you scatter particles or antiparticles. However, so from these three types of interactions, two of them are long range. So gravitational electromagnetic interactions, the low energy approximation is just the Coulomb potential. And this is because the particles that mediate these interactions are massless. Okay, so the graviton is massless and the photon is also massless. In the Yukawa case, we saw that we can add a mass to the force mediator, and this produces a finite range of interaction. Okay, so in principle, one can have massive spin 1 and spin 2 particles. So they will also mediate short range interactions. So the question is, can we have higher spin particles that mediate different type of forces? Well, the answer is yes, but they have to be massive. So massless particles with higher spins simply cannot exist. One can prove this as a theorem. So, well, I guess I'll stop here for today. Thank you for your attention. And yes?
And say the amplitude blows up for the P prime equal to P. Is it equivalent in the classical case as the Rutherford scattering cross section? I mean, the total when you do the integral it blows up.
Rutherford scattering, you mean electron photon scattering?
No, just the point. I mean, the charged particles scattering, the total cross section is infinite.
Oh, what scattering you're talking about? Which?
Just two charged particles scattering.
Ah, okay. So this is called Mueller or Baba scattering.
Yeah, I mean, is it? I mean, when there's a singularity there, is it equivalent to say that the total cross section goes to infinity?
The total cross section. Let me see. So. I think it diverges logarithmically. So something diverges logarithmically. When you study the cross-section in the Coulomb field, there is a... I know that if you study a cross-section of a particle, so here sort of particles are more or less equivalent, but if you study electron scattering on a nucleus, and in the Coulomb field of a nucleus, the cross-section will diverge as a logarithm. And that, again, has to do with this long-range nature of the Coulomb field. So yes, there can be divergences associated with it. Any other questions? Well, okay, then thank you for your attention, and see you tomorrow.